The last coordinate system we're going to consider is our spherical coordinate system. As we can see here with our spherical coordinates, we're going to use r, theta, and phi to represent points. Our spherical coordinate system is going to be useful for problems that have spherical symmetry. We're going to see later on in the course examples using things like spherical capacitors. So let's go ahead and draw our x, y, and z plane, or x, y, and z axes. And what I'm going to do to help me illustrate our spherical coordinates is I'm going to try to draw sort of an eighth of a sphere. So I'm going to try to draw a sphere that's going to help us be able to define a point in the positive xyz octant using spherical coordinates. So I'm going to mark spots roughly equidistant from the origin on our x, y, and z axes, and then I'm going to draw some little sort of arcs between the points. And so my z is a little high, so let me drop that down a little bit. So if you want to see a better picture of this, you can look on page 36 in the textbook. But let's see if I can get at least a half decent representation here. Okay, and then I'm also going to drop a point down sort of across what you can think of as sort of the front of this eighth of a sphere. So we have something that looks like this, and then this line is going to be useful a little later on. But let's say I have a point that I want to define, which is at some location here on our sphere. So this is, where do I want to put this? Let me put this over here. So this is P. Okay, so we already know we're going to have our R, our theta, and our phi. So let's do a similar thing we did last time with our cylindrical coordinates. Let me come down here and define these things explicitly and then add them on the plot above. So R is simply going to be the distance from the origin to our point of interest. So distance from origin to our point P in this case. So all we would do for that is, of course, we have some, let's do it in blue. So from our origin here, we go to point P, and that's going to be our distance r. Okay, our next sort of key parameter here is our theta, and our theta is called our colatitude. And so what our colatitude is the angle between the z-axis and the position vector of P. So here we're bringing up something that we talked about in chapter 1, or our first unit, which is our position vector. So we'll see what that is here in a second. So the angle between the z-axis and the position vector of our point, in this case our point P. And so remember, our position vector was basically just a distance vector between the origin and the point. So what I could do, for instance, this blue line represents our position vector. So I could write an arrow here, and that would be our position vector. So what we're saying then is that our, let me move this r a little bit. So let's put this as our r down here. So our theta is the distance or the angle between the z-axis and that position vector. So let's do that in red. So basically coming down from the z-axis all the way to this vector here is going to be our angle theta. So again, if we think of sort of, we have this slice of our sphere right there, our theta is kind of staying in that plane and coming down from our z-axis until we reach that blue line, which is our position vector. All right, so we've got our r and our theta, and then the last one is our phi, which is going to be the same as we had for our cylindrical. That's just our azimuthal angle again. And so our azimuthal angle, of course, is just the distance, or the angle rather, from our x-axis and our xy plane. So same as we defined in cylindrical. So in this case, if we come over here, we come back to blue, basically we're just saying from here to that sort of sheet, that's our plane within our sphere, that's going to be our phi angle there. So just like with last time, we can, of course, define unit vectors. So let me do, what color haven't we used? We've not used pink here. So our r unit vector is, of course, going to be extending along this blue line here. So sort of pointing out of our sphere, we have our r unit vector. So this would be u sub r, the hat. Our phi unit vector is just extending along that same sort of direction where our we're going from our x-axis towards our y-axis, so that's our u of phi, and then finally our u of theta is sort of coming down along this curve here. So we have something that looks like this. So that is our unit vector in our theta direction. It might be a little bit hard to tell how I've drawn it, but all three of these are mutually perpendicular. So these are mutually perpendicular unit vectors because we do have an orthogonal coordinate system. Okay, so let's also talk about the limits for some of these variables. So for our r value, similar to our rho, we see that it can't be negative, so the lower limit is 0 and the upper limit is infinity. So what that's saying is basically if we want to go in a negative direction, we just set an angle such that we have a positive r going sort of quote-unquote backwards. Now for our two angles, we want to be careful not to sort of include things twice, so we can't have 2 pi limits on both of them, but instead the way our textbook is going to define it is we're going to say that our theta ranges between 0 and pi, and that our phi ranges between 0 and 2 pi. And so notice for our limits on theta, both ends are inclusive, whereas for our phi, only one end is inclusive. So let's think about sort of what that is. So with our theta going from 0 to 2 pi, 0 would be an angle here, and then we're saying that can go all the way down, to pi, so we have sort of a semicircle almost that looks like that for our theta range. Now with our phi being able to go from 0 to 2 pi, that is sort of rotating around this z-axis here, so we can think about taking this sort of semicircle and rotating it around our z-axis to create a sphere. And then, of course, as we let that r go between 0 and infinity, we can, of course, reach any point we want. So that's how we define the ranges for those 3 parameters. Now, in terms of talking about vectors, of course, it's going to look very similar for as we saw with our cylindrical and our Cartesian. So if we have some vector A we want to represent in spherical coordinates, we can write that with our angle brackets. Now we're going to have an r component, a theta component, and a phi component. We could also write it as a sub r times the unit vector in our r direction, plus a sub theta times the unit vector in our theta direction, plus a sub phi times the unit vector in our phi direction. The magnitude, if we want to talk about magnitude of A, similar definition to the other ones, we just have square root of the sum of the squares. So square root of AR squared plus A theta squared plus A phi squared. So that would be the magnitude of our vector A. And then again, really briefly, we can talk about our constant coordinate surfaces. And if you want some more detail on this, again, you can look at section 2.5 in the textbook. But we just kind of think about if we set any one of these 3 equal to a fixed value with the other 2 being allowed to vary. So for instance, if we let r be constant, while our theta and phi can vary, we're going to have essentially a spherical shell. So we have a constant r, so we're always going to be some distance away from our origin, but our angle isn't fixed, so we end up with just a sphere centered around our origin. Now, if we had only theta fixed, what we're going to end up with is a cone. So we have some theta that's fixed here, but our r can vary, and our phi can vary, so we end up with something that looks like this, and it sort of circles around like that, and extends up in this direction, and so we get something that looks like that. Now finally, we can talk about our phi, which we talked about a little bit in our previous video, which would just be a semi-infinite plane. So this would be our phi, sort of our semi-infinite plane that extends in this direction. So that would be any r value, any theta value with a fixed phi. And again, we could talk about the intersection of 2, so maybe our phi and our theta. We could talk about that, which would be some line segment. we could have semicircles, and of course if we specify all three, that's when we get a particular point. But again, for more details on our constant coordinate surfaces, you can look in section 2.5. What we're going to do in the remaining videos in this unit is talk about how we can convert between our different coordinate systems for both vectors and points, and then we're going to look at a couple examples of how we actually do that and get some practice with it.